Okay, in this next segment, we will have a panel discussion. So we have gathered today a roster of experts in the field to pick their brains and learn their secret Sim2Real sauce. We will first introduce our panelists and then without hesitation throw our questions at them. We would love for you, the audience, to submit questions both in person, just raise your physical hand, or in Zoom, where you can raise your virtual hand, or by just typing out the question in the chat and we'll read it out. This is the perfect time to get your burning questions off your chest. And let's introduce our speakers. Here, physically, on the right, we have Viktor Makoviychuk. If his LinkedIn profile can be trusted, Viktor has been working for over 11 years on simulators for Nvidia. He was or is the tech lead for class simulation in physics and Apex, and he's worked on simulation on fluids and turbulences. Most notably, he's worked on moving robot simulation from the CPU on the GPU, and he helped develop Isaac Sim and Isaac Gym, the latter of which is currently speeding up my own robots experiment with by a ridiculous factor. Thank you, Viktor. Then online, we have Stefanie. Stefanie, are you there?
I am here. Hello.
Me in the spotlight. Okay.
Hi, everybody.
Hey. So Stefanie is an assistant professor in the computer science department at Brown University. The aim of her research is to construct robots that seamlessly use natural language to communicate with humans, with the ultimate goal of having household assistants. You could call her a robot whisperer because her most famous works are in getting robots to understand natural language for navigation and manipulation. Thank you, Stefanie, for being here.
Thanks.
Next up, we have Dorsa. You've hopefully already met this morning. In case you haven't, Dorsa is an assistant professor in the computer science department at Stanford and also a fierce debater. We also Ken, you've just seen, so for the sake of time, I'm going to refer to my earlier introduction. But again, let's welcome Ken. And Davida, are you online? Davida? Okay, David couldn't make it. Okay, then that is our panel for today. So I want to start with a stupid question to get this going. So you all know these would you rather questions, right? Like, would you rather fight a horse-sized duck or 100 duck-sized horses? So let's take this and put a bit of a topical spin on it. Assuming that you have funding for 5 years to build a new simulator, would you rather build one super high fidelity but slow and clunky simulator, or would you rather have 3 lower fidelity ones that are fast and easier to customize?
I'm a bit biased with respect to the simulation and performance. So my choice would be building one simulator that, depending on the task and load, could be very high performant, and GPU hardware accelerated, but also can adapt to more high fidelity or slow cases. So it's not one of them, but yes, and I think we can do it. Just using modern hardware.
Should I go? Yeah, so I would rather have 3 lower fidelity with the right representations doing the right thing that I care about rather than a single high fidelity slow that's not really doing the task. Yeah.
Let's you want to go last, Ken?
Yeah.
I feel like I'm the Wizard of Oz here, like hovering behind y'all. I definitely want the 3 lower fidelity ones because I think that there's a lot of uncertainty, and that's like more particles in my particle filter to try to find the right simulator and the right simulation framework. And I also think there's a lot of trade-offs that we don't even understand yet in terms of what representations to use and what needs to be simulated and what can be kind of approximated and stuff. So I favor more samples rather than fewer samples, basically. I would go for 10 if I could.
All right. Okay. Oh, sorry, go ahead.
Well, no, I really have nothing to add. I would say, I agree with I'd rather have
Is the mic on? Because I can't hear all of a sudden.
I'd rather have 3 or so, because I think that getting a universal simulator is tricky. Viktor, I'm actually curious why you would say it. So you would think the same simulator for, let's say, fluids would be the same simulator that you would use for robotic manipulation?
So as a starting point, it would be much simpler to implement only fluid and prototype different solvers, experiments, but eventually you want to perform more and more. So, okay, I have fluid, but what I can do? If I would like to do something robotics or more practical, I need coupling with rigid bodies. I need more and more features, and eventually we come into the states that we would like to have more general and functional simulator, even if we started from some particular and narrow tasks.
Okay, so while I have you here, just one last thing I'll ask is that, no, but what about non-determinism? Like, could you build that in? Because I think that would be really interesting with a simulator that would give you a number of outcomes, maybe weighted by probability.
Can you?
So it would have many outcomes. So with the same initial state, it would show you a number of possible things that would happen with different probabilities.
I would, if I'd like to have different outcomes, I would rather. I don't know how it can be possible to solve on the simulation level, but I rather have very parallel or distributed simulation, very similar to ones we have in Isaac Jim and working on, and try to run this distributed simulation with having the same object or set of objects, but with slightly different starting conditions, physical parameters, outcome, and we'll use rather performance and scalability to generate different outcomes.
All right. For the first, do we have any audience question already? Oh, Jesus Christ. Okay. Why did I even prepare stuff? Let's start here with Costas. Could you turn on the light at the front?
Are there suggestions for when should we get into simulation and when we should avoid it for try to solve a robotics problem? Perhaps someone working on Isaac should say, first always go to simulation, first try it. But do you have an intuition that perhaps some cases you would be wasting your time getting into simulation effort?
I think there's if it's okay if I start. I think there's like a real challenge in like getting diversity of data into the simulator. So like when you look at like all the different objects there are in the world, it's really hard. Like there was stuff like Ken's work with DexNet, but it's really hard to like get all the different doors and all the different drawers and all the different microwaves and all the different refrigerators into simulation in their full diversity so that you can actually generalize. Like I actually think that we need like a real effort to like increase the amount of different refrigerators we have access to in simulation, but also like trajectories of the robot trying to play with them in real life to kind of get to the next level of robustness in our robots.
Yeah, so just to add on that, I brought up this point earlier in the morning too. So we were looking at this problem of assistive feeding, and I argued that we don't have good simulators for deformable objects or food for a person's mouth, and we kind of like switched back from simulation to real world and actually like testing things in the real world instead of like touching the simulator. So I think it depends on kind of like what is the like how long term of a project we are looking at. If I was thinking, and I think Animesh brought up this point that maybe it is like a cop-out solution to just like work on the real robots, and everyone should be working on the simulation side of things, make the simulator better, make the simulator for deformable objects better, so we could actually solve that problem in sim and real. So it depends on how long term of a project we are looking at, right? Like if I was working on this, picking up food for the next 50 years, I would work on simulation, make sure that I have a good simulator, and then after that, like worry about the real robot, or like worry about the real to sim to real like aspect of things. But if I just care about like byte acquisition today, and I want to get a system that works with real patients in like 5 years, I would probably work on just real and not touch the simulators right now, because they're not like at the level that is useful. So I think it depends on how long term of a project we are looking at and what is the scope of it. If the scope, so then it only like picks up.
Can you repeat the
like,
question? Because we can't hear.
Yeah, so Kosta said, what is the point of having a simulator if you can actually solve like byte acquisition in 5 years without a simulator? Yeah, that's a very good point. So if I only care about byte acquisition, I think I can solve that without a simulator in 5 years. If I care about having a general purpose robot that can do byte acquisition, but can also maybe pour objects and steer objects and do all sorts of other food manipulations, then I think that is where we are going to see like benefits of like having a simulator, having more like generalizable scenes, generalizable types of action. So I think again, it depends on the scope of the problem. So if it is just byte acquisition, I would not use a simulator today.
Actually, I like your example, Dorsa, because I think that human behavior is so difficult to predict, right? So that's where you want to sample. Just as architects, sometimes they're not sure where to put the pathway, so they'll just leave an area and then watch how people walk on it, and then they build the pathway after the fact. So I like that idea a lot. I think one example, I mean, it just comes to mind again, Sharan's work with Flingbot, right? That's a very difficult. You're dealing with their air currents and a huge degree of freedom, very hard to simulate. So she did it directly in real, and that was, you were able to succeed. No, it's Sim2Real. Oh, never mind.
I mean, I think there's a little bit of a chicken and egg thing going on in Sim2Real. Like if you have a really, really good simulator and you can get the world into the simulator, then you can use that for planning, and then you can do things in real. But if you can't do things in real, then it sort of also means by corollary, you also don't have a great simulator, like to the degree that you're not able to do things in the real world.
So I would look and start this real world, not simulation, only in case if like I have a real time frame and the physics events I would like to deal with is hard to model in simulation, and there is no existing simulator. Otherwise, yeah, real world experiments are slow, hard, hardware can be broken, can be not safe for human, for robots. So for any other case, I would start maybe from simpler cases and from typing like learning pipeline or control in simulation first.
We have a question online from Animesh, actually.
Thank you for the shout out, Dorsa. I think all three academics, Ken, Dorsa, and Stefanie, said that they would prefer multiple simulators. And I'm actually slightly biased with Viktor. I would love to hear from you, the academics. What are you expecting in 3 separate simulators? Why 3 or why N? Would you not think that creating any simulator would require some amount of critical mass infrastructure for it to be practically useful? Is it because a lot of the effort that goes down these special purpose simulators often results in non-reusable, non-reproducible code as well. So could you describe what are you thinking when you're saying that like perhaps having N simulators which are perhaps special purpose is better? And could you also give examples? What would those special purposes be?
I think Ken and Dorsa already kind of alluded to like soft objects. I love Leslie and Tomas's example of like cling film, like saran wrap. Like, I think that there's a lot of, they're basically playing a trade-off between like your time modeling the physics of the world and your CPU time simulating the physics of the world and the fidelity of everything that's happening. whether you're going for photorealism or whether you want really good tactile feedback or whether you want it to run in real time, but you don't care if there's some inaccuracies. And so I basically think partly I want to be able to play at different points in that space. And partly I feel like we as a field don't understand how to do simulation well. I think that that we just like if we could just wave a magic wand and have the one true simulator that did it all, I would do it. Like if you're asking if I'm allowed to do that, but I just don't think that's going to happen. Like I think if they try to build the one true simulator, it's not going to be the one true simulator. It's going to have problems. And I think that the fastest path to the one true simulator, the simulator that's going to let us train the deep net, that's the equivalent of GPT-3 or something, and solve robotics. That simulator, I think it's hard to build, and we don't know how to build it. And the best way that we as a civilization almost know how to do research is to just have people try different stuff, right? And so that's why I think there should be end, because we don't know how. So people should make their best guess and try and make it and see how it works.
Okay, yeah. Yeah, so just to add on the point that Stefanie was making, I think, Animesh, it kind of goes back to the things that you were talking about actually earlier, like the different assets that goes into a simulator. Like you had a really good definition of what a simulator is and what are the different assets that goes into it. And the question is like, which one is missing and which one is it that we want to fix for a specific problem? So for example, like it might be like again, going back to food, right? Like the question is, what is the right representation of food that we would want to have if you want to have a simulator for various types of deformable objects like food? So I would want to have a simulator that focuses on various types of representations, like the right level of fidelity when we think about like those types of deformable objects. If you're thinking about driving, right, like I would want to have a simulator that can actually allow me to generate realistic driving scenarios, near accident scenarios. I don't care as much about the representation of like how a car is being represented. I care about the realism of like the type of scenarios that I'm seeing. So that's kind of like a different thing. Or maybe like if you care about generalization, like we might want to have diversity of data, right? Like maybe we want to open bottles of different shapes. So we want to have many different scenes, many different bottles. And that is something that I would want to have a simulator that allows me to generate diverse data. So I think we might have different goals when we are using simulators. And that is why like I feel like we might want to have 3 or n different types of simulators for these different goals. They're just very different goals.
Okay, thanks, Animesh. You just triggered another one of my pet peeves, which is the idea of universal to solutions. So I appreciate your point. I think it's really interesting, and I know that Nvidia is obviously putting a big investment in a general system, which is great because I think that all the interface aspects and efficiency aspects are going to be a benefit across the tools. But this is my same pet peeve about the idea that we build one network and one universal large model that's going to solve all these problems. And I just don't, and maybe it's my engineering side. I'm really rather solve one problem well than solve all problems. And I just don't think we're going to be able to do it with a general purpose network in the same way I don't think a general purpose simulator would really work well. It will overfit certain problems and grossly underfit other ones. So when arranged, if you're talking about manipulation, surgery is so different than, assembly in a factory. So you really want to have different simulators for that. I think, Animesh, although I'm curious would you argue against that?
I don't know if I should be answering this, but I think what Ken said is correct. And what I think when I use the word a single simulator, I'm not thinking a simulator for the world. I think that would be unrealistic. But I'm more with Viktor, where Viktor said a single simulation framework that can be adapted to either surgery or manipulation or food manipulation. Of course, driving is far too different a domain for it to be similarly shared. But I'll let others.
Also, I think the folks behind the Gato.
And I think, sorry, I couldn't hear. Somebody was talking.
Oh, sorry. Go ahead, Stefanie.
Yeah, I think that's probably where we'll end up. Like I would predict that once the things settle down, we figure out how to do it, we'll have a simulation framework with knobs you can turn and have different modes for different tasks, for example. And like, again, I think that probably parallels how our brains work and how our robots will work. Like we're going to have different skills and different models that are going to be really good for like food. And, I was just feeding my baby this morning and he made a giant mess with avocado everywhere, right? Versus like rigid objects versus clothes. You can imagine that there's different models and there's different, and some kind of hierarchical skill frameworky thing. And that's got to parallel the simulation architecture. I think that's where we'll end up as a field. But I think we're just not there yet. It's too soon. We don't know how to build that simulator yet. And I just think we need people to try different approaches and then one of them will, one of them will win. And then we'll all, in 10 years, we'll all be using Nvidia simulator, after we've tried a bunch of different ones. And we'll be happy.
All right. Fabio, I see your hand, but let me do another audience question first, then I get back to you. Let's see. Yeah.
So I'm interested in the idea of simulation accuracy, and the mechanical engineering and applied physics communities have some really, really amazing simulators, things like ANSYS and COMSOL and Abacus and so on. And they, simulate things like solids, fluids, thermodynamics. And what they do for accuracy, if they want to show people that this is believable, is that they have these verification manuals. And the verification manuals go through a long list, a really, truly extensive list of classic problems. Things like modeling spherical inclusions or flow between parallel plates or flow in pipes and so on. And these problems either have really well-known analytical solutions or they have really well-established experimental solutions. And I'm thinking that in robotics, it would be quite amazing for our simulators to also have some sort of verification manual, right? And in our community right now, we primarily evaluate the accuracy of simulators using policy transfer, where state transition dynamics are just one small part of the problem, right? I think it could be potentially really useful to think about physics. And I guess my question is, if you were to define some canonical, robotics physics problems for a simulator to evaluate, and if you saw that it performed well on those problems, you then would believe the simulator. What would those kinds of problems be? Can you list a few of them?
That's a great PhD topic. Seriously, that's a great point. I really like it. I think you're right. Benchmarks, in so many fields, we love to have benchmarks and we're lacking them. And having good simulation benchmarks is a great idea. And you could have data sets that were measured physically. And I like your other idea, which you have analytic. You would run all those things through the simulator and it would give you a good idea of how well it does. I think that's a great thought.
Yep, I agree with Ken. So we definitely lack some standard and good benchmarks in robotics, and it would be good to have such PhD, someone taking this topic. Also, I think that it's an interesting and physics simulation and research and topic by its own. But if we are talking about robotics, and it can be not totally correlated with successes, Sim2Real or policy transfer, and in many cases in robotics, actual success or policy transfers would be an example of success. And for example, having two different simulators, one very high fidelity but very slow, and another one say 10 times less so precise in particular situation, but much faster, the second one can be, despite less precision, the second one can be better actually for many robotics application, training robots, because it allows, scale is important in the Sim2Real robotics too.
It's a good question. I don't have a good answer for that. But one other point that I want to mention is the problem becomes even harder when you're dealing with like actual like human data. So for example, in the case of driving, right, you can have a car simulator where you have like cars driving on the road and you can kind of look at that and is that realistic? Is that not realistic? So in general, I've seen some work where they do kind of like a Turing test where they generate like driving data in this driving simulator and ask users like, does this seem realistic, like realistic driving behavior to you or not? Which is, I don't think it's like the best way of evaluating it, but I agree that's an important, difficult problem.
Yeah, I think you put your finger on like exactly why simulation and Sim2Real is so hard, is that you have to put the stuff in the simulator. Like you need a rich variety of benchmark problems. And I think the community would probably benefit if there was more richer stuff in simulation, like I said, like 1,000 or I don't know, 100 or 10, even 10 different refrigerators and microwaves and doors and drawers and light switches and stuff, you know. I also think the problem of like humans is a big thing. So like if you look at the dialogue community, like CMU actually ran a real dialogue systems for bus schedules. So like a person like could just call up the system and talk to the computer dialogue system and ask for information about the bus schedules. And then they use that to do research to understand like different variations of the computer dialogue system. But that's obviously a lot of work. And I think, you know, Amazon has done something similar with the Alexa challenge, where you can like talk to a bunch of different like Alexa bots. You know, injecting real human behavior into the simulation is another huge problem.
All right. Gonna sneak into this panel.
Yeah, just I have a negative reaction a little bit, Stefanie, to this idea of increasing more assets, and that this will be a big unblock for simulation, right? Because we want some of this to come from the methods to generalize, right? And we shouldn't expect that. We shouldn't put this aspect of the challenge on the simulation side, that it has to train on all of these variable objects in order for things to work in the real world. What do you think?
I think if you look at the other like the computer vision community, and you know, I'm more familiar with the NLP community, you know, these models love data, and the size of the diversity really, because we can collect you know, we can collect terabytes of data from our robots, but it's really the diversity of the data that we expose our robots to it's like there's a lot more zeros in the computer vision community and in the NLP community compared to us. Like if you look at like how many different objects we evaluate on, or how many different rooms, in one of our recent papers, you know, we were doing like 20 rooms, you know, and there it just, I think it's really clear that if we were able to do 100 rooms or 1,000 rooms, things are going to work better, you know, without too much different. Like if we just trained the model more on more data, things are going to be better. I think that's something we can learn from like what these deep models are good at. And I think the challenge in robotics is that we just don't have that data. Like the images that people take with their cell phone cameras is very, very different from the stream of data a robot gets from its camera. And it also is very different when you get to move your camera to look at different things. And that data is associated or paired with manipulation data, you know, and, you know, on policy versus off policy learning. So I think that there's like, you know, the extreme of like, you know, we just put everything in simulation and then it's done. I'm not advocating for that, but I do think adding some zeros to the size of our data set is almost a no-brainer in terms of making things work better. I also think it's important to like make more data efficient methods, because robots are a pain and running them for the weekend is hard. Like, you know, it's a hard thing to do. And so we want to be more data efficient, but I also think we should, that doesn't preclude also wanting more data. And I think the thing about simulation that's good is that we get more data. You know, we have the potential for more data without the pain of the real robot.
Yeah, I don't disagree that if we had more data, it would be better, and we should collect more data. Computer vision is in some sense ahead of robotics because they do have access to more data, but I think in some cases it's easier for them to have a lot of annotated data, which we cannot easily get when we think about 3D vision. And I also hate where computer vision community is going at the same time with these large, huge models to rule them all that only big companies can run, that get these huge resources in order to be able to execute them. And perhaps that's not the long way of solving our problems as well, especially because we will never
Yeah,
have.
I'm not like, I'm not in the, I like to contrast myself with like Yoav Artsy, who likes to make these really big black box models. I think that, when I get asked about that, I like to come back to Michael Jordan and Percy Leung's paper about discriminative versus generative models. I think there's this trade-off between the size of the model and the amount of data you need to train. And if you have a more powerful model with lots of parameters, potentially it can outperform the smaller model that makes more assumptions if you have enough data. But if you don't have enough data, the smaller model that makes more assumptions is going to be able to do better with less data. That's sort of the nutshell of the discriminative versus generative paper. But and I think in robotics, I think it's clear that we want to ride that, find that sweet spot where we're able to learn from less data. And I think the way to do that is to have structure in our models.
One thing I think, Stefanie, one thing I think is, remember Kepler, okay? There was a lot of data collected. And I've heard recently someone say, we should never throw out any data. Like, we should use every bit of data that we get. And, that was a perfect example where at a certain point, Kepler said, you can throw out all the data. We have a model and it works. And so you didn't need all those epicycles and all that, those observations anymore. So I think there is a danger, and again, it's generational, because I think some of the old guard love the analytic models, and that we don't want to. Some of my older colleagues were like, don't bother me with this neural net nonsense, but I think that's not right. But at the same time, the other extreme, we have to be a little careful about just thinking that everything's going to be solved and we're going to throw data. I see a lot of people looking at me with like daggers. Anyway, yeah, just because I do think there's going to be there are great models that are still yet to be discovered out there.
No, I'm on your side, Ken. Like, I think that, like, what I envision is, like, what I think is lacking kind of is really on the modeling side, like some kind, like I come from a POMDP perspective, right? Like we need some kind of like hierarchical model with objects and uncertainty that provides a structured hierarchical framework within which we can learn from these large data sets. So like, I work with George Kolidaris, and like the whole skills to symbols thing, like we have these big deep learned skills, but then we extract symbols, and then those symbols let you do symbolic planning and planning in a hierarchical way with objects and predicates and stuff. And then that all connects to language. That's kind of how I think it's going to go. But I just think, even with that bias, I think that we need more data. Like I don't think we're going to solve it with like a GPT-3 style, throw the kitchen sink at it and not think too hard about the structure of the model and just throw lots of compute. But I also think where we are now as a field in robotics, we need more data. We would benefit from more data. We're at the like inflection point of the asymptotic of the sigmoid, where doubling or 10xing the amount of data is going to give an inordinate improvement.
Sorry, before I get to you, Fabio, do you still remember your question?
Yes, I do. My question is the following, right? So when we talk about simulator, we are really considering multiple things, right? And sometimes it's easier for us to split into the several developments. So a simulator is an interface that allows us to, defines the states, defines how we communicate with the person who is using the simulator. So interface number one. The models. So these are the equations. It could be, from first principles, it could be learned. Then there are the solvers. These are the numerical solvers, the inference methods, and so on. And more recently, we're adding a fourth component, which is adaptability. How do we adapt simulators given real data to better reflect real data? There's another set of algorithms that go into that. Now, my question is that, and also connected to what Stefanie mentioned, we are at the moment where we can add a few knobs into this. We can make simulators that are faster, but less accurate. For example, by changing the way we solve the equations. Or we can make simulators that are slower, more accurate. We can also have models that are simpler or more complicated. Out of these four factors that I just mentioned, right? I'm just splitting the simulator into these four components. Which of those the panel thinks we should invest more energy into? If I had new PhD topics coming in, should I guide them to which of those?
Fabio, your question has caused concern.
Is it on? Okay, great. Yeah, I think I just came back from like another learning from offline demonstration workshop, and then we had this discussion like very similar about which direction the simulation should go. And I think actually there are multiple directions. So we talk about having this unified industry-wide standard benchmarks that we can evaluate the progress. I think for these benchmarks, mostly we're running evaluation on them. And in this case, the stability of the simulation and the accuracy of them will far outweigh the performance in that case. But on some other cases in simulation where we're trying to generate training data, in that case, the performance, the speed is matter much more. And we can just use some sort of randomization to remove some of the concern about accuracy. And therefore, I think both of these are valid. I'm glad to hopefully see more on the more accurate but less fast direction for simulators for robotics, so that we can build this unified platform to actually compare against across different labs.
Okay.
Comment. So yeah, it was a very good and deep question. So what focus development where to go? I have here one more proposal to it. So to focus or to look on development of differentiable simulators and to find to work on more precise physical models. So currently a lot of, I would say, differentiable simulation, very early stages, and most of what simulator use very simplified model, but this area is very actively development. So yeah, differentiable simulation using more accurate model, still taking into account performance and developing new methods how it can apply, and it would at least help to solve many questions, for example, about adaptability to the natural world physics parameters. And
so this is, I guess, maybe I should preface this by saying I'm a student still trying to figure things out, but I want to preface this with a question around like how a student or how a new roboticist should be using simulator platforms based on their field. So there's work like Ken mentioned around rigid assembly with rigid objects, which I think a lot of simulators are good for. There are harder questions like Dorsa had mentioned around assistive feeding with deformable objects. And there are even harder questions around human-robot interaction with assistive devices. How do I get a robot to hold a tray while someone is, picking a slice of pizza off of it? I want to talk about workflow and how students should be thinking about using simulators now and what you would hope.
I think the big answer is it depends. Like, what are you trying to do? And that really predicates how you should be using the simulator and whether you should be using the simulator versus not. For me, the big factors in making that decision are how good the simulator is right now, for what you're trying to do. And like, if you're trying to do something with HRI, with human interaction, like it's probably hard to simulate. So, you know, we try really hard in my lab to think about ways to leverage large data sets to train and evaluate our models, rather than trying to either simulate the person or do a small evaluation at the end with the real people. I also think, you know, in trying to figure that out, it's really important to be iterative. So like, rather than deliberating for a really long time about what the best way to use the simulator is, I generally recommend, let's try, you know, if you're not sure, just pick up a simulator and try to do something with it. You know, try to run a little model, try to train something, see how that goes, and let's talk about it. Let's look at some graphs, and then we'll iterate from there. So I don't, you know, George, some people are better, like George, my colleague, is really good at making really big, good, effective long-term plans. And I'm much more low level, like, let's just try it and see what happens. And like, I'm like Brownian in motion around the space. So something I would think about is like whether you like to have a bigger plan or whether you're like more opportunistic. I don't think one's better than the other, but sometimes if you, I don't know, it might depend on how well you tolerate risk and want to feel like you have a bigger trajectory versus not.
Well, what I would say is that I think it's a really good investment of your time to learn to use a good simulator. I don't think that will be wasted. If you, I mean, and Isaac Sim would be a great choice, I think, right now. That it's going to take a while of an investment to get comfortable, but doing that, and then I would say almost ideally comparing it with another, at least, so you have a couple that you can look at and see their strengths and weaknesses. That would be great. I don't know if that's taught in any courses that I know of. I don't know where that would be taught exactly. Maybe in ME, but I don't know if they would teach Nvidia. So yeah, I think that's a great investment if you're a student. I wish I had done that.
What simulator would you recommend? No, but honestly, like, you've seen, like, over your life, you've worked on different like parts of simulation, and like, as far as I know, not everything. Like Isaac Jim doesn't do fluid dynamics, right?
Isaac Jim doesn't do fluid dynamics. Isaac Jim and Omniverse, it's going to be supported.
Okay. There you go. There's your simulation to rule them all. Okay. Other questions? Yes.
Thank you. So this is a question from a curious bystander. I'm not in the field, but and it's about real to sim. So a lot of what Stefanie said jived well with me about how do we really make simulators better could come from a path from more data. I'm curious if you think that real to sim problem is a solved problem. If not, what research directions you think we should be taking?
I definitely don't think it's a solved problem. I mean, me and George are thinking about with our students about framework for like skills to symbols, where you basically start with the skill, whether that's somebody hacked the skill together or you learned something from demonstration or whatever, like, so you have a skill to open a door, and then you extract symbols from that with initiation and termination sets. So like, basically you have a thing that a detector, a classifier that goes from the high dimensional perceptual data of like, where am I standing and what do I see right now, to tell you, yes, I'm near the door. And I think if I run the door skill, it's going to work. It's going to open the door. And a termination, it's a similar thing. After I run the skill, I think I'm going to be here. And then that lets you do high level planning, which itself is a form of simulation, right? Like being able to plan to run these skills. It's like predicting what's going to happen if I go forward in space. And you can also imagine that that's like, you know, going back to what Ken was saying, probabilistic, like, you know, some of the, maybe I think 80% of the time, if I'm here, I run the door skill, I'm going to open the door, 20% I'm not, and I'm going to have to try something else, you know, try again.
So actually, well, that relates to, you know, one aspect is how do you collect the data from real? there's a really, I mean, really that gets into design of experiments, right? You have certain, you want to gain information. And so you want to run your next experiment to give you the most information about your model. And that's very hard to
Yeah,
get
so
out.
we have some work on that, trying to do it with augmented reality. So like, it's a really old problem of like the tour guide. Like you take the robot around and you give it a tour of the environment and it does something, and then it comes back and it knows something about the environment, right? I also think of it as like a dichotomy between like mapping and learning. Like SLAM itself is a form of learning, right? But we call it mapping. And I think if you sort of generalize the tour guide / mapping problem, you get a version of semantic mapping where like I'm making the occupancy map like I do now. I don't need to reinvent that. I can do that. And then maybe I give a demonstration to open the door. Maybe I drag the door 3D model over the real door in my augmented reality headset. Maybe I put on my VR headset and teleoperate it to open the door. Maybe I download, we have another paper about initializing the door skill from a motion plan demonstration, right? So then like I run my door detector and I somehow put the door URDF in the world, and then I run motion planning. So I get a crappy door opening skill, and then I practice a bunch of times on that door, and I learn a skill for that door to kind of bootstrap it. I do think it's actually, like, we were at a workshop at Google where they were asking, how can machine learning help HRI? How can machine learning help human robot interaction? I think the reverse question is also interesting and related to this, which is how can human robot interaction help machine learning by helping robots get this data that they need?
Add to that point. So just one more point on that idea of adaptation and real to sim. So I think that also helps us to figure out what is the level of fidelity of the simulator we want to actually like live at. So there is kind of this notion of abstraction and refinement from the field of formal methods, which is you come up with an abstraction. A simulator is really an abstraction. Imagine you have a traffic light with like a green light and a red light, but that doesn't capture everything, right? So you can generate adversarial examples that really require like a yellow light. And then you can kind of like go ahead and refine your abstraction and have like a new abstraction with 3 states of yellow, red, and green. So I think we kind of like need a similar type of refinement abstraction loop where we get examples, we generate adversarial examples for our simulator, we actually test it in real, and based on that, we go and fix our simulator. And that could potentially give us the right level of fidelity for whatever task we care about. Like, that's why I don't think we should have like a single simulator with the highest level of fidelity. Depending on what we want to do, like that level of representation might actually be different across the different set of tasks. And this real to sim can actually help with that.
I agree with that very much.
So your comment on adversarial work was spot on related to my question, actually. I feel like most of this, like many of these discussions we've been having about trying to increase the complexity of our simulations, the number of actions, the amount of data that we've been having, potentially Ken's earlier work on trying to do real to sim, on trying to select the parameters for modeling your environment. I think these mirror a lot of the discussions that were happening in the machine learning community 10 years ago, saying how do we get the data specifically that we want and not just general randomized systems. So one of the approaches that was popular, although I think it's fading, is the adversarial training approach, trying to select things select your parameters and your generative models as part of the training process. Seems like something that we could potentially do here. Have people been exploring that? Do you know anything about that?
Well, I think 2 things. One is that in some way you're right. It is a version of the same problem of taking the real data and fitting it to, fitting the simulator to it. The adversarial, I mean, maybe a GAN type of structure might be interesting to generate examples that would then challenge the simulator, or would actually be run in real, right? And then see what so you want to look for edge cases in real to see how they perform. This comes back to one thing that we haven't quite talked about is actually safety in real experiments, which is a big issue. And for example, we work with a surgical robot, and it's Da Vinci, and it's a $1 million arm, and it's very fragile, and so you could easily jam that into the table, and then you need a new arm. And so those are kind of things where you don't have the luxury of doing the adversarial actions, so you have to be careful about executing those. I think adversarial examples are fascinating, and constructing adversarial cases. I wish we did more of that in robotics. I've been doing a little work on adversarial objects for grasping, but I think there's a lot more of interesting cases that that will confound our existing methods. And that's another thing I think we should be doing as a field, which is really pushing for the failure modes and really seeking those out and being open about them as much as possible. Because those are, no one should ever be ashamed. And I think no reviewer should ever hold against an author for coming out with the failure modes of their work. That should just be somehow, I don't know, a principle in our field, because I think people are afraid to admit them because they're afraid reviewers will use it against them. But I think it should be just the opposite, that in a way you'll ensure yourself that the reviewer can't use it against you if you brought it up yourself. So anyway, I think that adversarial examples are very, very interesting and important.
Just to add on that, so in the space of autonomous driving, this is actually something that people are studying, like automatically generating test cases using like adversarial networks. The difficult thing is that you end up getting adversarial examples where your environment is a pedestrian and pedestrian is running towards your car, like going like 80 miles per hour, and that is an adversarial example. So it's not very realistic. So I think some of the challenges is how can you generate realistic like adversarial examples in simulation?
Yeah, I think the driving case is interesting because like so many times when we drive our cars, like if there was an adversary, you would be dead, like that flat out, right? Like if you're walking on the sidewalk and the car is coming next to you, they could just adversarially shoot you, like shoot over to the right and boom, you know. So I think it's a really challenging to generalize it to robotics. I think the models are very interesting though. In the language space, I'm not sure how to do it because I think the biggest problem for language and robotics is sort of generalizability, you know, just making the robot have a larger vocabulary. You know, I like to say people want to talk about everything the robot can see and everything the robot can do. And so then for me, as I've been saying, I think that comes back to diversity of data being the first order problem right now.
We have time for one last question. Sorry, the person behind you was first.
My question harkens back a little bit to the real to sim approach, which is like you guys alluded, there's always a trade-off between accuracy and performance in whatever simulator you choose. And our simulators are very good at incorporating the hard knowledge that we have from physics into the world, right? We know how things should behave. And so they are expected to work much better with a lot less data, like you said in the example of Kepler. So my question for the panel is, do you guys think that estimating accurate models with real to sim and then doing knowledge distillation could have a big impact in the performance of robots in the future? Like, does knowledge distillation have a big part in the Sim2Real, in bridging the Sim2Real gap?
So I'll let others speak about, when I hear knowledge distillation, I think of you're compressing your model down. So using latent representations, for example, latent state representations, I think it seems to be working extremely well. And that's a great point. I think that the same can be true for the model itself. You know, that we generally will pull off the shelf a 10,000 million parameter neural model, and rarely do you need that, right? So trying to reduce those and work with smaller models, distilled models, if you will, is a great. I think that will really help streamline the research and get concise, more accurate models.
Yeah, so the point of knowledge distillation is not just to shrink the models, but to make sure that maybe we could use those distilled simulators, right, to use classical control like MPC that have some guarantees and a lot of like literature behind them to perform the control instead of relying on, well, let's just train an agent and see what he does, right? So that's one of the big benefits that I see that could be possible with knowledge distillation.
I think we violently agree on this. Stefanie, do you want to add something to that? Did you?
I mean, I agree. I think shrinking models is good. Just that sort of distillation getting to some sort of symbolic presentation. I'm a fan.
Then, yes, let's thank everyone again, our panelists.